All right, today we're talking about a true classic, Pascal's Triangle. But more importantly, we're going to figure out how to find any number inside of it. Super fast. We're talking O of C time. So, have you ever wondered how you'd find a number way, way down in Pascal's Triangle without actually having to build the whole thing? I mean, who has time for that? It sounds like a total pain, right? Well, good news, there's a much smarter way. Okay, so first things first. Let's do a quick refresher on this famous triangle and lay out the exact problem we're trying to crack today. At its core, Pascal's triangle has this one super simple rule. It's kind of like stacking coins, you know? You start with a 1 at the very top, then every number that comes after is just the sum of the two numbers directly above it. See? 1 plus 1 gets you 2. 1 plus 2 gives you 3, and it just keeps going like that. It creates this really cool cascading pattern. All right, so here's the challenge. I'm going to give you a row, R, and a column, C. Your mission is to find the value at that exact spot. For instance, if I say row 5, column 3, you got to tell me the answer is 6. So what's the first way you'd think of solving this? Probably the most obvious one, right? Let's call it the brute force solution. Okay, the brute force method is basically doing it by hand, but with code. You start with row 1, that's just a 1, then you build row 2, then row 3. You literally just keep building every single row until you get to the one you want, row R. Then you just pluck the number out of column C. It sounds simple enough, but oh boy, it's not the best way to do it. Yeah, this is so inefficient. Seriously, think about it. If you need a number from row 100, you're crunching the numbers for all 99 rows before it, thousands of numbers you don't even need. That's like building an entire skyscraper just to see what color one single brick is on the top floor. It's crazy. There has to be a better way. And this is where things get really cool, because hiding underneath that simple add the two numbers above rule is a powerful mathematical shortcut, a secret that lets us skip all the hard work and just jump straight to the answer. So what is it? What's this magic trick that lets us calculate the value directly without building anything? And here it is. Every single number in that triangle is actually what's called a binomial coefficient. Don't let the name scare you, it's just a combination. So the value at any row R and column C is just R minus 1, choose C minus 1. That's it. Realizing this completely changes the game. So what's a combination anyway? Well, think of it like this. You've got a group of friends, and you need to pick a few to be on your team. The number of different teams you could possibly make? That's a combination. It's all about choosing items from a set where the order you pick them in makes no difference. Now, there's a standard formula for this, right? It's n factorial divided by r factorial times n minus r factorial. And on paper, that looks totally fine. But if you've ever done any coding, this formula should be screaming danger at you. And here's why. Factorials get huge. I mean, insanely huge, really fast. The factorial of 30? That's a number with 33 digits. Your computer's standard integer types, they can't handle that. You'll hit what's called an overflow error, and your answer will just be flat out wrong. So yeah, the formula is correct, but coding it directly is a recipe for disaster. Okay, so how do we get the power of combinations without blowing up our program with gigantic numbers? This is where we need to get a little clever. Instead of calculating 3 separate giant factorials, we're going to do it step by step. Let's use 4 choose 2 as an example. We'll start a result variable at 1. Okay, first step. We multiply by 4 and divide by 1. Now our result is 4. Next step, we take that 4, multiply it by 3, and then divide by 2. And we get 6. See how we're multiplying and dividing in each step? That keeps the numbers from ever getting too big. We totally sidestep the overflow problem. So the key takeaways here are use a loop, and in each pass of that loop, you multiply times and divide. Oh, and here's one last little optimization to make things even faster. N choose R is the exact same as N choose N minus R. So you can just pick whichever one is smaller, R or N minus R, and your loop will have fewer steps to run. Now that is thinking efficiently. All right, let's put it all together. What does this mean for performance? Well, the difference is pretty staggering. Just look at this. The brute force method, where we build every row, that's got a time complexity of roughly O of R squared. That means the bigger the row number, the way longer it takes. But our new optimized way, it's just O of C. The time it takes only depends on the column number, which is usually much smaller. We've gone from something that could take forever to something that's practically instant. The difference is just massive. So what's the bottom line? We now have a solution that's lightning fast with O of C time complexity. And even better, because we're not storing the whole triangle, the space complexity is O of 1. That's constant space. It doesn't matter how big the numbers get, it takes up the same tiny amount of memory. You really can't beat that. And this really gets to the heart of it. We stopped building the triangle and started calculating the value directly using NCR. It's a total shift in mindset from brute force to a smarter mathematical approach. So that leaves us with a question to chew on. Pascal's triangle is just one famous pattern. What other mathematical beauties are out there, just hiding in plain sight, waiting for us to find a more elegant, more optimized solution? It's something to think about. Thanks for tuning in.